This lesson is for FST, lesson 11.1 on normal curves. The parent function for the normal curve is typically referred to as a bell-shaped curve. Statisticians, mathematicians who study statistics, will call them a normal model or a normal equation or a normal graph. So know that curve, model, equation, and graph are all interchangeable in terms of its name. Normal models are appropriate when you're doing a distribution, and we did distributions in chapter 10. And in those particular distributions that are considered normal, they will be unimodal, which means one mode, and they will be symmetric. The parent function for the normal curve is this equation here. I just need students to just know that the equation was given to them. We're not really going to do much with the equation itself. The parent normal curve has some properties, however, that students do need to know, identify, and remember. So again, here's another picture of it, and some of the vocab has been labeled. It is symmetric about the y-axis, so that makes the graph even. That's something that students should know, that even functions are symmetric about the y-axis. If you don't remember what an odd function symmetry is, you should ask your teacher or a friend. It does have a horizontal asymptote on the x-axis. Many times, however, the book will ask you, or you'll be asked, to identify the asymptote in equation form. This is a description of where it is, but the equation for the asymptote is y equals 0. Y equals a number is always going to be a horizontal line, and the horizontal line is right on the x-axis, so it's y equals 0. The graph has some other characteristics that students need to be comfortable with. The first one is that it's concave up, meaning it curves upward or smiles at the beginning and the end. So that's here and here. So those are concave up regions. It's concave down, or frowning, near the x-axis. So that's this place here. And that should say, I think, near the y-axis, I believe. And then the last piece here is that it has inflection points, and those inflection points are where it transitions from concave up to concave down and vice versa. Students don't need to know much about inflection points other than the fact that they exist and that they exist where the concavity changes. Students will work more with inflection points when they pursue higher mathematics like pre-calc and calc. The standard normal curve is the one that we're going to focus on for a lot of the chapter. It is the most important offspring of the parent normal curve, and that's called the standard normal curve. Standard meaning real basic, real important, and it's the standard by which we measure other things. Why is it so important? It depicts the probability distribution of a standard distribution, which means that it's a distribution with a mean of 0 and a standard deviation of 1. Students do need to memorize that idea and commit it to memory. One interesting fact about the standard normal curve is that it has inflection points at 1 and -1. So those inflection points are easy to identify. Students don't need to do anything else with those other than say that they exist and talk about where they exist. This next one students should already know from our last chapter. The area between the curve and the x-axis is 1 square unit. If you think about the space covered by the graph itself, how much space it covers underneath, is going to be a 1. Or we talked about it in the last chapter as being 100% of the space covered. So when they talk about it in this chapter, they talk about the area between the curve and the x-axis, or the area under the curve is another way it's typically described. Normal models tell us how extreme a value is, and it indicates how likely you are to find that value and its distance away from the mean. So it tells you a way that you compare to others, particularly when we're looking at scores. The main thing that we're going to look at in this lesson is something called the 68, 95, 99.7 rule. As it turns out, in a normal model, about 68% of the values or scores fall within 1 standard deviation of the mean. What that means is 1 standard deviation above and 1 standard deviation below. So you can see that indicated here as the area shaded in blue. And you can see that it goes from -1 standard deviation to +1 standard deviation, so the whole thing in between is 68%. So it also takes up 68% of the space of the graph itself. 95% of the values will fall within 2 standard deviations of the mean. So that's the area pictured with the pink and the blue. So everything from here to here represents 95% of the space that's covered, 95% of the scores. And then 99.7, or almost 100% of all the values, fall within 3 standard deviations. That's the orange area all the way out to the very edge here. Before we move on, I want to help students divide this up a little bit further, because students are going to need to get really comfortable with these numbers and manipulating them to answer questions. First thing we're going to do is cut the graph in half. Remember that the mean is right here in the middle, and the mean in the middle cuts it in half. So if we were looking for just the lower half of the graph and how much space is covered to the left, wouldn't we say 50%? Obviously then everything above is going to be 50% as well. So get comfortable using the graph in halves. We're also going to start using the pieces that we were given in terms of the 68, 95, 99.7 rule. Since the blue section covered is 68%, if we cut it in half, obviously then this area would be 34% and this area would be 34, because that's half of 68. So then how would we find out how much space is covered by just the pink sections? Well, remember, the pink sections plus the blue altogether make up 95%. So if I take that 95% but I take away the blue region, that would be like doing 95 minus 68. And then because there's 2 of them and they're symmetrical, I would divide that in half. So what I end up getting for just the pink regions is 13.5%. So that's just the area shaded in pink. Each side is 13.5%. And then let's do the same thing to find the orange region. So the whole thing from orange to orange is 99.7. If I take away the 95, which is the pink and the blue combined, and divide that by 2, that'll tell me how much area is in between the second and the third standard deviation, which is currently shaded in orange. So the orange region is going to be 2.35 on either side. And then I still have everything past the orange region that I still need to determine. So I take whatever's left, so the 100 minus the 99.7, and I go ahead and divide that in half. That'll tell me what I have left, which I believe is 0.15. So now that we've got it all divided up, let's talk about some of the things that you're going to have to do. When you're working with a bell-shaped curve, and they ask you for how much space is covered from 2 standard deviations and above, you need to be able to be comfortable with this rule to figure out the answer. So if I know that 2 standard deviations above the mean is right here, and I want to know how much space is covered above that, I know that that's going to be 1 minus the 95%, because the 95% gets me from the negative 2 standard deviations below and the positive 2 standard deviations above. So the space that's not covered by the 95% in between is the 5% that's left. Since I only want the upper one, I would divide that in half. So from 2 standard deviations and up, wouldn't I say there that that's 2.5%? And that's a more typical answer than what's between 2 and 3. So most of the time we combine these two and just say 2.5. So let's include that on our sheet as well. 2.5 here as well. So now let's go ahead and apply these rules or these ideas to a practice question. So here's your example. With an average height of 184 centimeters, Dutch males are among the tallest in the world. That must be some statistic that someone has gathered. If a normal model exists and the standard deviation for their height is 8 centimeters, what percent of Dutch men are over 2 meters tall? One thing to keep in mind here is some of the factors are in centimeters, some of them are in meters. So let's convert the meters to centimeters. Common knowledge idea here is that there's 100 centimeters in a meter. That would not be a question I would answer on a test or a quiz. That's just general common knowledge. So since there's 100 centimeters in 1 meter, there's 200 centimeters in 2 meters. So I'm going to convert that number to 200. Usually when I have kids do questions like this, I encourage them to draw their own bell-shaped curve. The mean should go in the center where the 0 would normally be, and then let's actually find the values for 1 and 2 standard deviations. They're asking for over 2 meters tall, so I'm not going to worry about going below. So one standard deviation above the mean would be 184 plus 8. So hopefully you know that that would be 192. And then if we go 2 standard deviations above the mean, we'd add another 8 onto that and we'd get 200. So that means the 200 centimeter tall person is 2 standard deviations above the mean. We want to know how many people are over 200. So we are indeed looking for everything above the second standard deviation. So I know that the whole thing is 1. If I take away the 2 standard deviations, which is pink to pink, that's the 95%, I'll get 5%. But I don't want both of the pink answers, I just want one of the pink answers. So I divide it by 2, so there's my 2.5%. That's one way to do it. There are many other ways, but that's typically what most people do is they think about, okay, 2 standard deviations, that covers 95%. I only want to know what's above that, so that's 5%, but I'm only looking at half of that because there's 2 of them. So half of 5% is 2.5. Let's try another example. Suppose it takes you 20 minutes on average to drive to school with a standard deviation of 2 minutes. What you can think about there is when most people talk about that in real life, they say give or take 2 minutes. That's what that means. And a normal model is appropriate. How often would you arrive at school in less than 22 minutes? I'd recommend that you draw your bell-shaped curve. And again, you put your average in the center. And then let's draw some standard deviations. Standard deviation is 2, so the next one up is going to be 22, the next one up is going to be 24. We're looking for less than 22. So I'm looking for this number and then everything below that. So hopefully you remember that this first chunk here from the mean to the first standard deviation is 34%. And I know that from the mean back, that's going to be 50%. So all I need to do is do 50 plus 34 there. There are other ways to answer that question, but I believe that one would be the easiest. So we'd say 84% of the time you're going to arrive to school in less than 22 minutes. How long would it take you more than 24? More than 24 is going to be from here and up. So that's the same as the Dutch mail question that we did earlier. That's going to be 2.5%. They may ask you some vocab questions like, do you think the distribution of driving times is unimodal and symmetric? Unimodal and symmetric are 2 characteristics of the standard normal curve, and this clearly is a standard normal curve that we're doing, so we would say yes here. So students need to complete the worksheet, and I'll scroll through this momentarily for the video in case you didn't get one in class.